This video is part 1 of section 1.3 of the Math 311 course on linear algebra. This is on lines and planes. Part 1 will mainly focus on lines. Now, lines are something we are very familiar with, hopefully. I want to start with hopefully a very, very familiar example from your high school algebra class. Finding the line in R2 passing through 1, 3, and 3, 7. And you were probably, hopefully you all know how to do this. You start by finding the slope, which is the rise over run, which is the change in y divided by the change in x. Okay, so this becomes 4 divided by 2. Now, normally what we would do in class, we would simplify this to 2, and that would be our slope. And then we would find the equation of the line. We'd pick a point here. I'd use point slope form, so I'd write y minus 3 equals the slope times x minus 1. Okay. Do a little algebra, and this becomes y equals 2x plus 1. Okay. Then maybe you would draw a picture for it, and then you'd be done with it, right? Well, there's a little more to the story now that we're doing linear algebra. We'd like to say there are actually many ways to represent this line. There's only one way to write this in slope-intercept form, but we're going to say we can actually write this in vectors and use do it many different ways. So first of all, we can note that xy is on the line if and only if the vector xy is equal to the vector 2x plus 1. Okay, that's nothing, that just comes from this. But we can actually break this up as a linear combination of vectors, 0, 1 plus x times 1, 2. And if you think about, well, we'll just add this up. This is 0 plus x times 1. This is 1 plus 2x. So that's what this is. So this works. And hopefully you can also see that x can be anything. Just like we could plug any number in for x here, we could plug any number for x here, right? So we can just say, instead of calling this x, we can call this any number, any symbol we want. So I'm just going to call this t now. And I'll just say for some real number t. Okay? All right, now we've represented this line by a vector equation. Now I want to show you there's nothing unique about either one of these two vectors, because if we go back and look at this line, so this is the graph of y equals 2x plus 1. So here's 3, 7. I'm sorry, 1, 3. Here's 3, 7, and here's xy. I'm going to call this vector connecting these 2 points D. Okay. And we can see that so D, what is D? Well, we basically kind of computed it up here. We just have to get the x, do the x's first. 3 minus 1 is 2, and 7 minus 3 is 4. Okay, and we're going to call this the direction vector of this line. And obviously the vector connecting these 2 points has to be a multiple of D. Okay, and what is this? Well, this is x minus 1, and this is y minus 3. And so it has to be a multiple of D, a scalar multiple of D, so we can just let t be this our scalar, and then this will be 2, 4. And we can break this up, and what we get is that xy is going to be 1, 3 plus t times 2, 4. Okay? Now, compare this equation and this equation. They determine the same line, but we just have a different parameterization. That's what the parameter is. Notice that over here, we can expand this out to get 2 equations from this vector, and here we get x equals t, y equals 1 plus 2t. Here we get x equals 1 plus 2t, and y equals 3 plus 4t. And here the point 37 corresponds to t, the value t equals 1. Here 37 corresponds to t equals 3. Okay. So this gives a slightly different parameterization, but it gives us the same line. Okay. Now, one other thing before we move on from this example is that we know, again from high school algebra, that a line that's perpendicular to our line here, because this has slope 2, a line perpendicular to this will have slope -1/2. Okay. But let's suppose we didn't know that, all right? And let's say we have this line here, and we just know it's perpendicular. And let's say this point is 1, 3. Let's say this, we can choose it so these lines intersect at 1, 3. We know the direction of our line here, if this is y equals 2x plus 1, the vector here is d, which we already said is 2, 4. And if we call this vector n, the direction vector of this line, the direction of that is, well, we know that these vectors have to be orthogonal, which means their dot product is 0. And there are lots of vectors that would work, but one thing we can do is we can, because it just has length 2, we can interchange these two components and multiply one by -1. So we can let n be the vector 4, -2. Okay, these have to be orthogonal because their dot product is 0. And now what we have is, now if we take this vector xy, or a point xy on our first line, and then let's say consider this vector from 1, 3 here, this vector is going to be orthogonal to n as well. And what is this vector? It's x minus 1, y minus 3. This is orthogonal to 4, -2, so their dot product is 0. And if we multiply this out, this is 4 times x minus 1 plus -2 times y minus 3 equals 0. And if we multiply everything out here, we get our original, and simplify things, we get our original equation, y equals 2x plus 1. So we're right back where we started. Okay. So here we've represented the same line a number of different ways. We can represent it as an equation involving a dot product set equal to 0. We can write it as parametric equations. We can write it as vector equations, or we can also write it in the traditional general form. And that's what we have. To summarize what we have, this happens in any line in R2. Right? We have a point. We're used to having a line being determined by either 2 points or a point in a direction. And we know that from our work we've done at the beginning of our first example, we can always get this right. The equation of a line as something times x plus something times y plus something, and that's general form, right? That can be reduced to slope-intercept form or whatever form we want. But we can see that because that the vector connecting any 2 points on the line has to be a multiple of this direction vector, d, which we can always, the direction vector is not unique. It depends on what the components are not unique, okay, because they depend on what 2 points you pick. But the actual, so we get these a, b. We can just call this a, call this b, and then we can see that this minus this is this vector that has to be a scalar multiple of AB. That's where this t comes in. So this equals this for some real number t. So xy is on the line if and only if this equation holds. And once again, we can break this up and to put everything on one side except for the xy, and we can get we have a vector equation. And we can get, if we give this vector and this vector and this vector a name, this vector is x hat, this vector is p hat, p for point, and then we already know that this was d. We can actually write this as just using bold-faced vector symbols. So both of these are equations, are examples of a vector form of a line in R2. And by equating, just writing down the corresponding components, we get the parametric form. And then finally, because we know that this vector b minus a is orthogonal to d, as well as any multiple of d, which is to be denoted by td, so we have this equation. Remember, x minus p is the, that's what this is, where p is x0, y0. So this is 0, and then if we can multiply this out here, so we have b times this plus negative a times this equals 0. We distribute, and we get something like this. Once again, we get some number, something times x plus some number times y equals some number here. Remember, x0 and y0 are just numbers, whereas x and y are variables. Okay, so we're right back to the general form. All right. So let's, now, we can generalize some of this stuff to R3, okay? In R3, just as in R2, 2 points will determine a line. Okay? And so, it's just that we have all the points have an additional coordinate here, right? So once again, we can take 2 points, we'll find the vector that connects them, and then that's the direction vector of this line. You take any two other points on this line, the vector connecting them will be a scalar multiple of d. Okay, so we can compute d in the same way. This is x1 minus x0, y1 minus y0, z1 minus z0, and we see that the point x, y, z is on the line if and only if the difference, this expression, x minus x0, y minus y0, z minus 0, that's this vector right here, is a scalar multiple of d. So it's equal to t times abc for some real number t. We can break this up and put it in this form, right? And so we have x is equal to p plus td, okay, where again x is this vector and p is this vector. And we can get a parametric form of this. Basically, just by equating all the components, we get 3 equations now instead of 2. And so we get a parametric form. You've probably seen this in Calculus 3, hopefully. Okay. Now, there are some differences. There is no normal form or general form for lines in R3. Okay, let's just think about why that's true. Reason why is because, first of all, with normals, things have to be orthogonal to each other. And because we are we have an extra dimension here, there are going to be lots of vectors which are orthogonal to this line. Okay, right. So you can't. There's just not one. It's not like one vector will work. There's going to be a whole lot of them. In fact, in R3, we want to talk. It makes more sense to talk about planes being orthogonal to a line than just a line being orthogonal to a line, right? So we can't define. We can write a similar. We can write a similar form like n dot something, x minus p equals 0, but this actually defines a plane. Defines a plane which we haven't started talking about yet. Okay, and similarly, if you have something like x plus y minus z equals 2, that also defines a plane. Okay. Parallel lines. Parallel line in R2, two lines either meet or they don't. So that means if they don't, they're parallel. Otherwise, they meet. Of course, in 3 dimensions, it's possible you can have non-parallel. You can have lines that are that might not be and have the same direction, but they might not meet. For example, you could have a line which is always above where the z coordinates are always above another line. Okay, so the directions would be different, would be quite different, but they would not meet. So that's the difference between parallel, non-parallel, parallel lines in R2 and R3. We're going in R3. We're still going to say that parallel lines are parallel if their direction vectors are multiples of each other. Okay, so so I guess the definition of it would be that if D1 is some scalar multiple of D2, then the lines are going to be parallel. Okay. All right. Now I want to get an example here. How would we find the equation of a line, or represent the line in R3 given 2 points? All right. So here we have 2 points. We have 1, 2, -4, and 3, 0, 1. Okay. And we can first find our direction vector here, D. What is it? 3 minus 1, so that's 2. 0 minus 2, -2. And 1 minus -4, that's 1 plus 4, that's 5. Okay. All right, now for P here, P is just going to be the coordinate. It's a vector, but it's also just going to be the coordinates of one of the points. So we can pick any point will work. We're going to pick 1, 2, -4. Okay, and so we get that, using the this form here, we get x is equal to P plus TD. So this is x, y, z equals P. So P is going to be, we just said is 1, 2, -4 plus T times D, which is 2, -2, 5. Okay, that's the vector form. And then the parametric form would be the corresponding 3 equations. Okay, and that's all there is. Again, there's no general form, or there's no normal form for lines in R3. Now we can talk about some other applications. We can talk about angles between lines. Okay, if they, in particular, we're talking about lines that intersect at a point. Okay, what does their angle look like? So if we have 2 lines like this, we're interested in the angle between them. Now, I think you can see this boils down to finding the angle between 2 vectors. Okay, because this line is going to have a certain direction vector D1, and this has a direction vector D2. So and if you remember the formula for finding the angle between vectors, it's actually the formula for the cosine of that angle. And if you remember, it's D1. In this case, it would be D1 dot D2 divided by the length of D1 and the length of D times the length of D2. Okay. And in this case, you don't really need to know what the point of intersection is. Really, you just need to know the direction vectors. Okay. So in this next example, example 3, let's say we wanted to find the angle between these lines given by y equals 3x plus 17 and y equals 2x minus 2. We're in R2. I should emphasize this. squared in R2. So we just have to find the direction vector of each. And in this case, we can obviously see the slope is 3. Okay, and if the slope rise is 3 that's rise over run. Okay, the rise is 3 when the run is 1. So the direction vector of this would be 1, 3. And similarly, since the slope here is 5, the direction vector here would be 1, 5, right? Okay, and so the cosine of theta would be the dot product of this. This would be 1 times 1 plus 3 times 5 over the length of d1 times the length of d2. And this is 16 over the square root of 1 squared plus 3 squared, so that's 10, I think. And the length of this would be the square root of 1 squared plus 5 squared, so that would be 26. And this is where you use the calculator. This is approximately 0.99228. And so you take the inverse cosine of that, and so theta is approximately 7.13 degrees. Okay. That's what's going on here. All right, and then you can do the same thing for lines in R3. Just do the same thing with vectors, as long as you know for a fact that they intersect. Okay, and this is where we get why we know what we know about the slopes of perpendicular lines. So in high school algebra, you were told, well, okay, you just take the negative reciprocal of the slope, and that gives you the slope of a perpendicular line. And they never told you where this minus comes in or the reciprocal comes in. Well, it comes from this. It means it says if M1 and M2 are slopes of perpendicular lines, right? Then that we already know what the angle is. It has to be 90 degrees. And once again, D1 will be 1 M1, and D2 will be 1 M2. And so 0 is the cosine of 90 degrees, which is D1 dot D2 divided by the lengths. Okay, we know that this is never going to be 0, so the only way that this can be 0 is if the dot product is 0. Okay, and the dot product is going to be 1 plus 1 times 1 plus M1 times M2 equals 0. So M1, M2 has to be negative 1, and so M2 equals negative 1 over M1. Okay, so that's where the negative reciprocal comes in. Okay, prove it from using dot products. Kind of cool, maybe. All right, we go to the last example, or the last sheet. Going back to finding the shortest distance between two lines, we can, and again, we're working in this first case in R2. Now we have to, it doesn't make any sense to talk about the shortest distance between the lines unless they're parallel in R2. If they intersect, then of course the shortest distance is 0, right? And these two lines, we know that these are parallel because they have the same slope. And you might think, well, the difference, 5 minus 1 is 4, so you might think that the distance is always 4, but it's not quite true. And you have, if these are parallel lines, we know that this distance is always going to be 4. But what we're really interested is in what is this distance right here. Okay. Well, the way we can do this is we can use our projection, our friend the projection. Because all we really need to know is, we already know the direction vector of both of these lines, right? The direction vector D is going to be 1, 2. we can easily find 2 points here that on each line. And the easiest way to do this is just plug in x equals 0 here. You get 0, 1. Plug in x equals 0 here, you get 0, 5. And if we call this vector v, then v is going to be 0 minus 0 is 0, and 5 minus 1 is 4. Okay, and then what's going on here is that we want to find this distance, but we start by finding this vector here, that is again the projection. We're projecting v onto d, right? Because d is the direction vector of this line. So it's projection of v onto d, which is, remember, the formula. It's d dot v divided by d dot d. Okay, so in this case, the dot product here is 8. Dot product here is 1 plus 2 squared. 1 squared plus 2 squared, that's 5. Okay, so it's 8/5 times, and of course we have to multiply this by d. So d is 1, 2. So this is going to be 8/5, 16/5. Okay, so that's the projection. That's this distance right here. But we want to find this distance, so we want to find what this vector is. Okay, and remember we have this vector plus this vector is equal to v. So if we call this w, remember that w is going to be v minus the projection. So this is 0, 4 minus 8/5, comma 16/5. Do a little arithmetic. This is 0 minus 8/5. That's negative 8/5. And this is 20/5 minus 16/5, so that's 4/5. And one thing that might help us before we actually take bring out the square roots, we can factor out a 4/5 out of this here. And this leaves us with a negative 2, 1. And we can clearly see that this and these are orthogonal. So that's good. And so the length of w is just going to be 4/5 times the length of this vector, which is, again, this is going to be square root of negative 2 squared plus 1 squared, which is 4/5 times the square root of 5, which is 4 over square root of 5, if you want to write it this way, or this is approximately 1.79. Okay. So that's actually, so that's this distance, and that's the shortest distance between these two lines. I am going to leave you to do mainly work on this next one on your own. I will say this, you basically are doing the exact same thing. You have these two lines in 3 space, find 2 points here, and then you want to find this distance by first finding this vector, projecting this onto the direction vector, and then taking the difference and then finding the length of that difference right here. You can see that in this case, these are the lines that are given in vector form. This tells us that the point 0, 1, 3 would be the first point, would be a point on the first line, and negative 5, 2, 0 would be a point on the second line. And we can see that, notice that the direction vector in both cases, oh, that's very nice, they're both 2, 1, 1. Okay, so that's D. V is going to be negative 5 minus 0, 2 minus 1, and 0 minus 3. Okay, and then at that point you get I'm going to let you do this, finish this up. You basically do the same thing we did up here. We compute what the projection and then the difference in the length, and it's going to turn out that the distance is the square root of 11. So I will let you work through that and check my work. And so this is all about lines. Next lecture we'll be talking about planes, and in the next lecture after that we'll be talking about the connections between the two. Okay, thank you.